Well, welcome everyone. Thanks for coming. It's great to see so many of you, some of you again from last year. So I'm David Anthoff. I'm from UC Berkeley, and this is going to be an introduction to the Queryverse, a family of packages that I've created over the last couple of years that live in sort of the data science, data stack area. So this is the outline that I have for the talk. So we'll start with some logistics. Then I'll walk you through one end-to-end example that just showcases most of the parts of Queryverse. And then we'll dive into individual parts. But I wanted to start out with an example that showcases how everything works together. And then we have sort of various topics that we'll cover as we go along. OK, so in terms of logistics, so this is in the style of a tutorial. So it's meant to get you up to speed on how to use the Queryverse. The scope of it is essentially tabular file, so you can load various file formats and save various file formats, all sort of that are tables. There is data manipulation with query, so that was the original idea why Queryverse came about. So query, if you're familiar with dplyr, for example, or with link from C#, that's really the two inspirations for that part. Query gained, or the Queryverse gained a plotting package, BigAlight. So that's in collaboration. That's not actually, I didn't start that package. I just contributed over the last year to that one. And Data Voyager is a data exploration tool. So I'll show both of them. But we now have an integrated story for plotting that's very much in the spirit of ggplot. So a grammar of graphics interface for plotting. And then the Queryverse at its core has an interface for tables. So it essentially works with anything in Julia land that has the format of a table. So this is sort of not restricted to data frames. It, of course, also works with data frames. But it also works with pretty much any other table type. And there are other interesting table types in the ecosystem. And so I'll talk a little bit about how that works. In terms of prerequisites for this talk, so this is not a Julia tutorial. So I'm assuming you are somewhat familiar with Julia. I don't assume that you're familiar with the typical data manipulation workflow along the lines of dplyr or something like that. But if you are, that will probably make things a lot more interesting. All right. So setup. If you want to follow along, you can follow along on JuliaBox. Everything, all the packages that you need are installed on JuliaBox. If you do, there is a folder on JuliaBox. I think it's tutorials and then intro to Queryverse or something like that. And if you run your code in there, it will automatically you will have access to the files that I'm going to load as part of this example. If you want to follow along on your local machine, these are the packages you need to add. If you start now, it's probably too late because you all know the joys of our old package manager and and precompile times, but this is sort of what you would need to follow along your tutorial, the tutorial here. So I either listen or follow it along on JuliaBox is probably the best strategy. I should say one thing about 0.7. I had really hoped that I could port everything to 0.7 before JuliaCon. That did not exactly pan out. I'm this close. So if you are on 0.7 already at this point, this will not work because there's still a few things to be ironed out. But I'm close. So I think it should only be a matter of a couple of days, and then this should all work on thank you. There you go. Excellent. On 0.7. All right. So now I have my script, which is also helpful. All right. So let's start with the end-to-end example. So this is sort of just showing off how everything works together. And so let's go over to, all right, so we need to end the slideshow here. And then it shows up here. And then let me create a new, so what I'm going to do is I'm going to create a new Jupyter notebook here. And that's where I'm going to do everything. Is this big enough, or should I can increase everything a little bit like that? Can people see that? OK, so I'm going to start out by loading the packages that we need. Maybe a word about that. The Queryverse package is a meta package. So it actually doesn't, it hardly has anything in it. It just loads all the other packages that make up the Queryverse jointly. Vega Datasets is a package that you can think about it like R datasets. It's just a package that exposes a bunch of datasets. Those originate from the Vega project, so that's what that does. And then index table, some of you might know, is a table type that was created by Julia Computing, I believe, that powers JuliaDB at this point. So it's just another table type that one can use. And so now I'm wondering, why is my kernel not running here? Let me see. So it says kernel is connected. What's happening here? Okay, let me try a new one, because I think something here is not right. Shut down. Let's delete this. Let's create a new. So while we're waiting for this to decide to come alive, I'm going to use Jupyter Lab here, which is the next version of Jupyter Notebook. And it's been really reliable over the last 6 months, and now it's letting me down here. OK, so let me just kill everything and try new. I also wonder whether this has something to do that I'm not in the Wi-Fi. OK, so I'm in the right folder. All right. OK, I think now we're good. Using Queryverse, using Vega datasets and indexed tables. Yes, OK, this is looking much better. So I think now we're just waiting for the usual Julia package load times. I don't think it hangs. Yeah, OK. All right. So we're going to use a specific data set, which I'm assigning to a variable called cars. I'm extracting that out of the Vega datasets package with the dataset function. And this is how this works. So I'm dataset, and then you can pass the name of whichever example dataset you want to use to the dataset function here. So that's what it looks like. It is some dataset about cars. And these are the columns that we have here. And I've now assigned this to the local variable cars, or actually global variable cars here. So the first thing that we're going to try is we're going to look. We want to get a sort of sense of this data set quickly in a visual way. And for that, we're going to use the package data Voyager, which was loaded by the Queryverse package. So this is the one example that will not work on JuliaBox, because you actually need to run this on your local machine. So if you're on JuliaBox, don't try to follow along. This will not work. So what we do here is we start out with the cars data set, and then we pipe that into the Voyager function. So this is a pattern you will see over and over again in the Queryverse, that we pipe things, data sets, through different manipulation stages. So here we only have one. So we pipe it directly into Voyager. And so what does that do? It opens up a new window that gives us in one view a first glance at this data set. Okay, so it automatically creates one plot or visualization for each column in our data set. It looks at each column and tries to find out what is a meaningful and useful type of graph for that column. So for example here, it automatically detected that there might be something about years. So it automatically created a plot that utilized that information. For the others, it's essentially creating histograms. So we can very quickly get sort of a first glance of the data that we're looking at. So let's say we want to go beyond just looking at individual columns here. We're looking or hunting for patterns in this data set. So what I can do here is I can drag and drop this field here where it says quantitative fields onto the x-axis. So what I'm saying with that is take all the fields in my data set that are quantitative columns and put them on the x-axis. Okay? So I have a whole bunch of the columns here that are numbers. So it's actually going to create one plot now for every column that is quantitative and put that on the x-axis. So now I can drag the same field, quantitative fields, on the y-axis as well. And automatically I get a whole bunch of scatter plots where I'm scattering every column against each other column. So this is and I'm only scratching the surface of this tool here. It's really cool. You can do lots of other things. You can say, I don't know, I'm always get confused about all the options you have here. You can say, for example, you can put the number of cylinders in the color field, and then automatically a legend is added to each plot here, and the number of cylinders is put into is used for the colors, and there's sort of a gazillion different options that you can use here. This tool here is built by a team at the University of Washington, and they're a large team. I think there are a couple of people that are working on both the visualization side of things and this interactive data exploration tool. So the only thing I did here is I exposed this to Julia. Okay, so this is one way, one aspect of this. I'm going to close this again. But it's useful for sort of quick data exploration if you have a new data set. Another core feature of query or Queryverse is actually querying itself, where you take a data set and you want to manipulate it in a certain way. So I'm going to give you a quick example of that. So we're going to start out with cars again. And now I'm going to pipe it into a data manipulation verb. So I'm using the pipe operator, and then I'm creating a new line for each stage in my data pipeline that I'm going to do here. And so here I'm just going to filter things. So I'm going to use the filter command from the query package. And I'm passing in here a condition that will be applied to each row in my source data set. And I can reference each row with the underscore. And then I can reference the columns with dot and then the name of the columns. So here I'm going to say, I only want to return the rows where the origin column has the value USA. And then I'm going to pipe that result set. So actually, we can look at that really briefly. I can execute that. So now we have a table where a couple of rows were filtered out. And now I can continue to pipe this filtered data set into, say, some CSV file. So I pipe it into the save function, and I'm going to save it as US cars CSV. So this is the core idea here, that you build up these data pipelines to manipulate data, and then you can have various sort of things that you can put into these pipelines. Let me show you one more example of one of these pipeline ideas. So we're going to load the CSV file that we just saved. We're going to load that again, and then we're going to create a plot with this CSV file. Not using this interactive visualization tool that I just showed you previously, but with an API for creating plots. So I'm going to say load uscars.csv. So this loads a CSV file from disk. And then I can pipe that into my plotting command, which is vlplot for BigAlight plotting. I'm going to say I want to create a plot with points on it. So the first argument here is the type of mark that I want to see on my plotting surface. And then I can bind or encode which column of the data set should correspond to which aspect of the plot. So here I'm going to say the x-axis should be miles per gallon. The y-axis should be weight in pounds. And then the color should be cylinders. And here I'm doing a little twist. I'm specifying the name of the column as a string, and then I'm adding :n, and by that I'm indicating to the plotting library what type of data cylinders is. And so here I'm saying it's nominal data, and that will determine how the plotting package will actually visualize that. So I execute that, and it should create a plot here that looks like this. And the plotting package here that is used with this vlplot command is the same plotting package that is powering this interactive visualization tool that I've just shown you. So you get the same visual aspect of that. OK, so I think that was sort of my very quick example to show you sort of the scope of what this is. I'll get to you in a second. So it's essentially tabular file I/O. You can load and save tabular data to disk. You can create visualizations, both in an interactive way and then with code like here. And then you have query where you can manipulate tabular data. So that's sort of the scope of Queryverse. And so the rest of the talk, I'm going to dive into each of these aspects in more depth. But before I go on, there was at least one question. And I should actually say, I would encourage you, if you have questions, please raise your hand, and I'll try to address them as we go along. Yes?
Yes, so the question is, if cylinders were categorical, then would it automatically detect that it's nominal?
No. So so the question was, if cylinders was a categorical data type, would BigAlight automatically detect that? So so there's some detection logic in here, but it is not perfect. So I think if it was so it's not integrated with the categorical data type from Julia. But if it was a string, for example, it would automatically classify it as a categorical data type. But the one thing it does not do is pick up an order that you might have specified in a categorical value here. Any other questions so far?
You said :n was what?
So cylinders, if you look at the data here, is actually a numerical column, right? So it's numbers here. But I actually want it to be plotted as if it was a categorical type here, so that we get a different color for each value that we have in that column. So let me just show you what happens if I don't do that. So I can remove that here. So I just specify the column name. And in this case, it's actually using a scale here that is a continuous scale, because it thinks, oh, these are numbers, and you probably want them on a continuous scale. All right.
Why, sorry.
Yeah.
So you have quotes there, but you have symbols elsewhere.
Yeah. So what's the story here? So you can use a symbol wherever you could use a string. They're interchangeably, so it doesn't matter. But you have to use strings if you want to use the :, something, because that is not a valid symbol. So in general, you can start out with a symbol because you save one character. And then if you need to be more expressive, and there's actually more syntax in this here that you can use, then you need to go to a string. So I should say one thing. So the BigAlight package, BigAlight is created by the University of Washington. It's a very expressive plotting language, but it's very verbose. Okay? So I spent about a year trying to go from this very verbose syntax to something where a simple plot like this is not verbose. And it took me a long time to do that. But I think I've really found a mix now between, on one hand, having a short and concise syntax for simple plots, and then a very natural extension to the full power of BigAlight, where you can go completely crazy and be very expressive in what you can specify.
The question
Yes?
Can you use a command for 3 variables as well on a 3D plot?
So there's no 3D support in this. And I think the reason for that is sort of a cultural. It seems that the people that live in the stats plotting world, which is very much inspired by ggplot, don't like 3D plots. And so, I'm not saying that BigAlight is the plotting package for everything. I think it really lives in the space of ggplot, sort of statistical grammar of graphics type plotting. If you want 3D plots, don't even look at it. Okay, another question. Yes.
Can your macro get confused if you actually want to use symbols or strings to specify something else? So not column of the data, but say a column which you want to use.
Sorry, can you repeat that?
So can the macro get confused between using a symbol to specify a column on your data set or a symbol to specify some other quantity like a column that you want to use?
No, that is sort of sorted out. So what you specify here is always a reference to a column. And if you wanted to specify a value here, okay, why don't I show you that in a second. So there's a way to specify a value that is distinct. I'm actually not going to show that to you because it's a bit in the weeds. But no, it does not get confused. Yeah. Okay, so why don't I continue with my script here. And let's go back to my slides. So the first thing I wanted to talk about, or the next thing I want to talk about, is the file I/O story that Queryverse supports. So let's start out with the types of files that are supported by it. So these are all the files formats that are integrated right now with Queryverse. So for some of them, you can load them but not save them right now. Others you can load and save. So you have CSV files, obviously, Feather files, Excel files you can load. You cannot write them right now, but I think we now have all the pieces in place that could actually be added relatively simple. There's support for 3 different types of stats files, data, SPSS, and SAS. Again, right now only read support is there, but the underlying library I'm using now actually supports writes, so it should actually be relatively straightforward to add that as well. You can read Parquet files. The FST files format is very planned, so that is probably the one that is furthest off. And then there's support for bedgraph files, and I don't even know what they are. Someone else in the community added that, so you can read and write them. And all of that is sort of behind a unified API for reading and writing things. Yes, Scott has a question.
Would you then recommend using the Feather format for if you're wanting to save and load your data using Queryverse? If you have data that you created yourself, performance things.
So what would I recommend of these? Probably Feather is a good format if you want to save something on disk for a couple of days and then go back to it. Yeah, that's probably the best format for that.
There's a CSV, you've got all the parsing.
CSV is obviously not an ideal format, right? I mean, I guess the strategy would always be, if you get something in CSV format, you have to deal with it, unfortunately. And you might have to save it as a CSV file if you interface, if you hand it off to someone else. But I think for your own workflow, Feather is probably the best format, yes. Okay, so those are the formats we have. Now, all of those are exposed through a unified API to users. And it's really a simple API. It's actually the API from the file I/O package. So it integrates with that. And so there's a load function. And you pass the file name that you want to load to that function. So that function actually originates from file I/O. And you can pass, if you want, arguments and keyword arguments, so that for some of the file formats, you can control certain aspects, especially for CSV. You can sort of control things like what's the character that's delimiting columns and things like that. And that will return a table always. Okay? So if you pass a file name to the load function, and it's a file type that is a tabular format, then you will get a table back. So what do I mean by you will get a table back? So I will not tell you what I mean by that yet. I will talk about that later on. It's not a data frame. It's not actually one single type, but conceptually, in sort of in a logical format, it's a table. And so then anything in the Queryverse that can consume a table can consume what you get back from something like a call to the load function. And later on, I will explain how that actually works. But for now, it's enough to just think about this as a table. So that's the load framework. And then we have a save framework. Very simple. You call save. The first argument is the file name. The second argument is anything that's a table. Again, this is not restricted to data frames or any specific type. Anything that sort of follows the idea what a table is in Queryverse will work with that. And then you can pass in arguments and keyword arguments. So that's the first way in which you can call the save function. The second way is that you can use this pipe that I've shown you previously. So you can have something that is a table, and you pipe it into the save function. You pass in a file name, and then depending on the extension of the file name, it will automatically save the file in the correct format. So this hopefully makes for a very simple API for users, so you don't really have to think much about which package do I need to use for which file format. It's for all the tabular file formats here have the same user-facing API. So I think I'm going back to code now to just show you that this actually works. This is going to be a bit tedious, but I've spent so much time on getting this to work that I will torture you now to show you that it actually works. OK, so let's start out with loading a CSV file. So I say load data cars CSV, and it loads a CSV file. I can load a feather file. I can say data cars.feather. So this is just let me show you that. Here in files, there's a folder that has data in various file formats, and I'm going to load all of them now. So here I'm loading a feather file, and it's returning a table with the same data. Let's load an Excel file. So I'm going to say data cars.xlsx. Now, for an Excel file, I actually need to tell it which sheet I want to load, because an Excel file can have multiple sheets. So here I have to pass in a second argument, and that's the name of the sheet. So if I just pass in the name of a sheet, it will automatically detect where the table data is on that sheet. So that also works. I can also, with Excel files, I can specify the range from which I want to load explicitly. So here I can say, from the cars sheet, I want to load from C1 to G41. So this is the normal Excel range syntax here, by which I'm specifying an exact rectangle on the sheet cars, and then it will load that. And apparently, there's a mistake. 41, yes. So that, all right, there we go. OK, let's continue with this, because it's so much fun. I can load cars DTA. So that's one of the stats files, and I always forget which format that is, but that also works. I can say data cars SAS 7B dat, which is another stats file format that works. I can say data cars SAV, which is another stats format that also works. And I think that's all I wanted to show you at this point. OK, so that's the load functionality. Now, the next thing I'm going to show you is the save functionality. That's going to take a little less time, because we only support saving at this point for 2 file formats. So I will torture you a little less. And I'm going to show you both this invocation here and this invocation down here. So we're going to start with the cars data set. Remember, that's the one that I loaded from the Vega dataset package. So that's the example we will mostly use here. So the first way to save this here is I can call the save function. I say cars1 CSV. So that's the file name I want to save it to. And I pass in cars as the second argument. And so now if I look here in files and I refresh this, then it actually saved the file here as a CSV file. The other invocation type here would be that I pipe cars into save, cars2 CSV, and that would also work. So if we refresh this here, we now have a cars2 file here as well. So for CSV, we can specify a couple of options here. So I can say cars save as cars3 CSV, and then, oops, no, that's not what I wanted to do. And then here I can say, for example, that I want to use a semicolon as the delimiting character. So if I now look here at cars3, it actually, the Jupyter CSV viewer does not auto-detect that. So if I switch this over to a semicolon, then it shows that properly. OK, and then obviously you can also save things as feather files. So you can say cars4.feather, and it should save everything as a feather file. So if we look here now, then there's a feather file here. OK, now you can obviously combine those. So you can do something like the following. You can say load data cars SA7BDAT. So I'm loading a table from a stats file format here, and then I'm going to save it as a CSV file, CSV. And that will also work, because this here, on the left-hand side of the pipe, produces something that's a table. And the thing on the right-hand side is something that can consume a table, and so you can just pipe it through. Note that in this case here, there's actually never a data frame or anything like that allocated, right? It goes directly from the source file format into the target file format. OK, that's sort of all there is about file I/O. Any questions about that? Yes.
Yes. So just the last comment. But what is allocated? Is it passing it row by row, or in blocks, or it has to read in everything into the memory?
So the question was, what is being allocated here? Is everything sort of read into memory first and then saved out, or is it row by row? So the interface that I'm going to describe in the next slide, actually, that makes all of this possible is completely streaming. So it does not require anything to be loaded into memory. And then whether that actually happens end-to-end depends on the specific file format implementations that we have. So for some of them, you actually would end up with a completely streaming exercise where nothing gets loaded into memory, and it's just loaded on demand, row by row, and then saved by row. But in this example here, for example, that's not the case, because the library that I use to load the stats file actually loads everything into memory first. So the architecture is there to have everything streaming, and then we just need to improve the implementations. Yes, another question.
For the parsing call to work, does it mean that the call to save returns the function itself?
Yes. How is this here implemented? That's the question. Yes. So if you call the save function with just a file name, it is returning an anonymous function that takes one argument, and that will then actually save things to disk. So that's how the piping here works. So it's a currying story. There was another question, yes.
A similar question on the pipe. So the pipe operator in R uses the first position by default, and you have to specify with a dot if you're going to do like not first position. So in your case of save cars, like the first line, line 17, you want the cars second. So how do you figure out, like, you're specifying a non-standard?
Yeah, so this is not like, the way the pipe works in Julia is different from the way the pipe works in R. And so I'm just reusing what the way the Julia pipe works here. It has nothing to do with a positional thing. It really, the way it works is if you call save with just a file name and not a source, then what it will do, it will return an anonymous function, and then and then the pipe operator will call that anonymous function with whatever you pipe into it. And so it's a currying implementation, and that's how this is implemented. That's sort of just the standard Julia way of doing these things. It does have an implication, and that is this does not automatically work with any function you want, right? So the thing on the right essentially needs to support this pattern here. So that's different from what we have in R. Any other questions? OK, so the next thing I want to talk about is I want to go into this question, what is actually a table in Queryverse? Because I've sort of hinted at, Cortona is showing up here. All right. So what is a table in Queryverse? Because a table in the Queryverse is not a single type. It's actually an interface that I've defined a couple of years ago. And then I provide implementations, or a lot of packages provide implementations that implement that interface, and that's why everything can talk with each other. So what's a table in the Queryverse? The interface that I'm using here is called an iterable table. That's the name. So if a type or a function supports that, then it can interface with everything else. The interface is defined in a package called table traits. And so, yeah, so that looks like that. It's a very simple interface under the hood. It's essentially just an iterator of named tuples, for those of you who are familiar with that. And because it is so simple, it was actually relatively straightforward to add support for that interface to almost anything in Julia. So right now, this is sort of the universe of packages that speak that interface and support this interface. So anything in any of these packages will just work with each other if you've loaded Queryverse, and will play in this game of this is a table. Okay. So there are a couple of ways to structure this a little bit more than just sort of throw out a large universe. I'll get your question in a second once I'm through that. So one thing is that some of the packages that you see up here natively support this table traits interface. So the package authors themselves said, OK, I want to add support for this. So those are the packages in green here. So all the green packages out of the box in the code of the package support this iterable tables interface that's defined in table traits. For the other packages that did not want to take a dependency on that, I created a package called iterable tables, which essentially patches the iterable table phase onto those packages. So that's one of the things I was very careful about designing. It is not required that you derive from anything or anything like that. So the way the iterable tables interface is designed is you can actually add it to a type, even if the type didn't opt in originally. And so all of these integrations then for the blue packages live in a package called iterable tables that's maintained by myself. And so if you load that, then all the blue packages all of a sudden also participate in this interchange here. My hope is that at some point iterable tables, the package will die because all the packages have decided to natively integrate with this. But that's not where we are right now. From a user's point of view, there's no difference where this comes from. And packages like Queryverse or Query just load the iterable tables package by default. So I think from a user's point of view, this is sort of an unimportant aspect of the story. If you just load any of the packages, everything will just work with each other. We can also structure this a little bit in terms of what types of packages there are. So all the green packages here are the various table implementations that are around. So certainly the most popular one is data frames here. There are the table types that Julia Computing created, index tables and JuliaDB. There are some specialized table types for time series data, temporal and time series. There's the pandas package that wraps the Python pandas package. And then there are some older typed tables and data tables that I think are both end of life, but that are still working actually with this story. Then we have all the I/O packages. So those are the native Queryverse I/O packages that I showed you. And then it also works with any package that implements the data streams interface. So all the great packages from that universe, especially on the DB side, for example, also work with this story. Then it's integrated with a couple of plotting packages. So Gadfly, BigAlight, and StatPlots all work with this. Data Voyager is the interactive exploration tool that I showed you. TableView is a package that shows data frames in a grid. So those work. It's integrated with the Query package, obviously, and then with stats models. So those are packages that provide analysis functionality. And then it also, and then there's this odd one out, differential equations. Chris sort of, I don't know, I think it's probably 2 years ago, or a long time ago, Chris added support so that the a solution of a differential equation actually is an iterable table. So but it's handy, right? Because essentially what he got for free was all the file I/O and integration with plotting and so on. All right, so that's sort of how you can slice and dice that. I think you had a question. I've answered it. Okay, excellent. All right, so let me see what I wanted to do next here. 1 second. I just need to figure out for a second when I wanted to move on to the next slide. Okay, I think I want to do code again now. I hope slightly confused with my own script at this moment, but it will all work out. So let's explore this a little bit more in detail. So let's load a CSV file here, cars.csv, and let's pipe it into the typeof function to get a sense of what is actually the type that is returned if you just do a load call here. And it's actually a type called CSV files that's defined in the CSV files packages. What happens if I load a feather file, cars.feather, and I pipe it into typeof? It actually, the type of that instance is a feather file. What happens, remember I have this DataSet function that returns something from the BigAlight Vega datasets package. So that's not a file I/O package, it's a package with a bunch of datasets. No, I wanted to pipe that into the typeof as well. So that's yet another type. So all of these functions here return different types, right? So they don't return a sort of a unified type, but all of these types implement the iterable tables interface, and that's sort of how this then works. So what can I do with something that returns something that implements the iterable tables interface? Well, I can pass it to any function that accepts an iterable table. So one of the functions that does that is the constructor of data frames after you've loaded my packages. So you can say load data cars.feather. So what does this mean? This load function here will return an instance of a feather file that implements the iterable tables interface, and then you can pass that to the data frames constructor. It knows how to deal with an iterable table, and it will construct a data frame out of this. We can also generally use the pipe for this type of story here. So I can say load data cars feather, and then I can pipe it into a data frame, and we'll do the same story here. But that's not, that's sort of one of the things we can pipe it into. But we can also, for example, pipe it into an index table, because index tables also understands the iterable tables interface. So I can say data cars feather, and then I pipe it into a table, which is a function that creates an index table, and that should also work. So now I've piped the data into an index table. So now we can do silly things. This makes no sense. I'm just sort of showing things you can do. So we can load something as a feather file. We can pipe it into an index table. So this creates an index table, and then we can pipe it into a data frame, right? And this will work, and in the end we will have a data frame, because all of these support the common interface, and so everything works. There was a question, yes?
Yes, so how is checking if a type supports the interface implemented?
So, okay, the question was how can you check whether a type implements that interface? Can I actually hold that question, because it is quite, it's not straightforward. I will tell you one thing: it is not based on dispatch. Okay, I'll leave it there. I think maybe we can have a chat afterwards, yeah, okay. Because it's slightly more complicated. So you can also obviously do the other way around. So I can. So these are my silly examples. So you can pipe it first into a data frame, then you can pipe it into an index table. That also works. So all of these things can just sort of interrupt the way you want. We can do things like this. We can say load data, cars, feather. We pipe it into a data frame. Now we pipe that into a plotting command. So I say x equals horsepower, y equals acceleration. So that works because data frame is an iterable table. BigAlight plot understands that. We could have taken the same thing and we could have plotted an indexed table. So if I just replace that with a call to table here it loads a feather file, it converts it into an index table, then it plots the index table. That works exactly the same way here. But of course, I actually don't have to materialize it into a table type at all, right? I can just take this one out directly, and I can pipe it from the file directly into my plot command, and that will obviously also work. And then, obviously, this also works with any other format. So I can say, here I'm loading a stats file, and I'm piping it into a table. So I get an index table that I loaded from this stats file here. And then we could convert the iterable table here into a data frame again. So you can go back and forth between all of this in any way you want. I think that the main benefit you have from all of this is that any individual table type actually becomes a little bit less important because you can use the table type that is best for your specific application. And I kind of like that idea. I think that's sort of one of the benefits that we have in Julia, that we might actually have table types that are specialized and good for a specific thing. So I don't know, the time series table types, for example, specialize on one specific niche aspect. But now this allows you to quickly then put it into a data frame again, or load it and save it and so on. So all of these types can sort of get a lot for free by integrating with this. You can also, so here, let me just show you another thing here. So IT here is an iterable table. I can pipe that into my data exploration tool, the one I showed you previously. So that will open up a new Voyager window here, the interactive tool. That obviously also works with data frames. I can pipe a data frame into the Voyager tool. I can save an iterable, an index table into a feather file. So that works. I can save the data frame into a feather file. So it, that you can just go back and forth between all of that. So the question now is, how is this done under the hood? What's actually the interface that supports all of that? And that's my next slide. So the first thing, there's no abstract supertype for anything here. And that was sort of a very conscious design decision early on, because I realized if I require things that want to integrate with this to derive from a type that I define, at that point I've lost half the packages, right? Because people want to have their own object hierarchy. So this is not based on an abstract supertype. The interface is actually very, very minimal. It's essentially, if something is an iterator of named tuples, where each named tuple is a row, then that's it. Okay? There are a few minor twists to that are not super important, but sort of broadly speaking, if you have a type and it can iterate named tuples, you're good. If you have a function that can consume an iterator of named tuples, you're good with integration here. There are also some other interfaces that can make things faster in certain situations. They're optional, so if both the source and the sink sort of support them, then in theory things might get faster. But at the core, it's really this iterator of named tuple interface.
So
yes?
Named tuples, that's new in 07? Or
oh, yes, that's a good point. So there's a named tuple package on .6 that has powered this for 2 years or so. It was a really great package. Without that package, someone else created it. None of this would exist without that package. And then on .7, we have native tuples that are in Julia itself, which is even better. So I should say, I think one aspect about this interface is very stable. It's been around, I think, for almost 2 years now. I've not changed anything about it. I've moved the definition from one package to another at some point, but other than that, there has been really no change to it. There are no real changes planned. I mean, I think Jacob and I are trying to integrate things a little bit with data streams, but I think the core of this interface is not going. I don't see any need to change anything about it because it is so simple and basic. And I think that's sort of a good thing about this. So if you ask Chris, who integrated EQ, 2 years ago, he did that, and then he never had to do anything again, right? Because I just left him alone. And I think that's sort of an important part in this package ecosystem, that we don't have this constant churn of sort of things changing. This is really stable and solid, and if you integrate with it, then you will not, I'm happy to help you once, and then you will not hear from me again for a couple of years. Yes?
I have a question. If this interface assumes that the type of named tuple is constant, which might be relevant if you do streaming and you find out only after reading 10 millions of rows that something is not the type you thought.
You have good questions. The question is an assumption built in here that the fields in the named tuple always have the same types. So as you stream, can the type of a column change, essentially? And the answer is, in the current implementation, it assumes that everything stays the same, so that there's no change. There is, in theory, I think this is sort of more or less an implementation question. So iterators have a way to signal that they don't have a specific type. So if the trait for has element type says no, then I think it would actually be valid to return different element types. And then it's more or less a question whether the sinks can handle that. So I think that they don't at this point, but I think it would be completely feasible to think of a world where we don't have to change anything about the interface itself, but where we improve the implementations of the sinks to support that scenario. Yes?
So when you change between these different table formats, do you reinterpret the types of the elements or the columns, or do you assume they're the same? Do you copy the...
So it's a copy. So if you iterate through something, and then you materialize it in a new table type, it creates a copy of everything. I have sort of started with a couple of other interfaces that if both the source and the sink speak that other optional interface, they can use a more efficient interchange format than this iteration of named tuples. That is sort of early days, and it's not there yet. And my idea is, so my focus right now is really to just get everything to speak with everything. And then I think to get more efficient interfaces for special cases can be optional opt-in. But I think the core important thing is to have one basic stable thing that does not change anymore for the most simple interop. And then, data streams has, for example, supports scenarios that I don't, in a much better way. And so if both the source and the sinks speak that, then they should use that, right? But I think there's value in having one simple, most basic, least common denominator interface so that everything always works with each other, and then some things will be faster and others won't. Yes?
If this may actually touch exactly that point. The thing I've been having trouble with when using this ecosystem for large amounts of data, usually with columnar storage and only needing a few columns, is that materializing the whole tuple usually kills my performance because it kills SIMD optimizations. In actually very few simple cases, the compiler manages to optimize it all out, but in typical real-world cases, the compiler does not manage to optimize it out. Is there a road to getting to those use cases where you have large amounts of data, you select a few columns, you have an efficient binary background store, and you want to really run full SIMD and everything?
There is, but it's not implemented. So, I don't want to spend time here to sort of, but I'm happy to chat afterwards. It would be a fair bit of work, but the architecture is there to support that kind of scenario. Yeah. Okay, so one thing, the interface is fully documented, so if you want sort of a spec for that, And then I think this slide really, from a user's point of view, hopefully it doesn't matter, well, except when ugly performance problems show up, but that's the idea here. OK, so that was the story about the iterable tables interface. The next thing I wanted to talk about is the pipe. And you've seen it, and maybe I'm going to go a little bit faster for that one because it's also relatively obvious how that works. So the broad idea here is that you start out with the source, and then you pipe it into various data manipulation stages. So you build up a pipeline of steps that you want to apply to your data. So the data from source gets passed to the step 1. Step 1 will manipulate it in some way. The output of step 1 then gets passed on to step 2, and that way you can build up these pipelines. So let me just show you that. Just in terms of sort of conventions here. So one, you can either, so I'm going to load something here. So here I'm going to do a filter. So this is sort of a preview. I've already shown you that from Query. So I'm filtering out certain rows, and then here I'm going to pipe it into a data frame. So you can either have everything in one row, in one line of code, or you can break things out over multiple lines, and especially if you have pipelines that sort of have multiple steps, that is often much more it's easier to read. So normally the way I structure my code is like this, that I indent the subsequent steps on the lower line, so you can build up these pipelines here, and sometimes they become long, right? So you might have a 10-step pipeline or something like that, and then splitting it out into rows is a good idea, I believe. OK, so let me show you another. Let's actually copy this here, and but instead of piping everything at the end into a data frame, I'm going to save it into a cars10 CSV file. So what I'm doing here is I'm loading a CSV file, I'm filtering it, and then I'm saving it as another CSV file. So note now that this save function here doesn't return anything. So it's not. So there are two types of steps that you can have in a pipeline. Some return something, and then you can pipe that into the next stage. Others have just side effects. So write something to disk or something like that, but then don't return anything. And so the save function is an example of that. But maybe we actually want to continue our pipeline here. Maybe we don't want to stop at this point here. And so there's also support for that. So if we can build up pipelines in the following way. We can wrap a step in the T macro. And this is sort of the T command from the Unix shell here. And what does that mean? So the source gets still piped into step 1. But then the next step, namely step 2, does not get the output from step 1, because step 1 actually doesn't have any output. But the source gets actually also piped into step 2. So the T macro essentially means, in terms of the pipeline, skip this step. Okay? So you can have a step in here that saves something to disk, and then continue your pipeline with the thing that came before that step. So my hope is that at some point I can convince the Julia core folks to add another pipe operator that does that thing. So that would be awesome. My hope would be pipe and then 2 of these, I don't know, things or something like that. But right now you have to use this T macro for that. Yes?
So are there any restrictions what can be used inside a T? So is
Nope.
it okay, can I T into an operation that returns something?
Yes, but that return value will be
lost, yeah.
lost. Yes.
That's what I want.
Yes. Yeah. No, there are no restrictions on that. Yes.
Is it possible to put additional frames inside the team?
Yes. I think so. I don't think there's any reason why that wouldn't work. Brave words, right? Never. OK, so let me give you an example of that. So I'm going to say load. So actually, let's just copy this code from here. So here I'm going to just put a T around this save function. And so now if I run this, I actually see the table again because the return value of that whole expression has a return value again because the save function that sort of eats output is no longer what's being returned here.
Can you show just briefly what is the type of the returned expression here?
Here?
Yeah.
Sure. So I pipe it into type off. It's a query, an enumerable filter. It's an internal object from query. So I'll go into that later on, but what filter returns is an object that is an iterator that filters things.
Yeah,
and
so
that's
it's lazy, yeah?
It's lazy, yeah, everything's lazy. Yes?
If the source supports it, let's say it's a database, can filter offload that to the source? Is there a path to something like that?
Yes and no. So one of the core designs of query is to support that scenario, so that if you write a query against a SQL database, that the query actually gets translated into SQL and then runs in the database, right? Because it's sort of silly to load everything from the database into memory and then filter out half the things again. And that part of the design is directly copied from LINQ from C#. And I have an example of that working, and it works exactly for one specific narrow query. But it's enough as a proof of concept to show that that is possible, but I don't have the time right now to finish that implementation. If someone wants to take that up, it would be fantastic and awesome, but yeah. Okay, so let me show you an example with this T story here that is more interesting than the type of. So let's say we want to save this filtered CSV data set, and then we want to plot things. Horsepower. So that works now, right? So we saved things. The T made sure that the data that was piped into the save function actually gets continued in the pipe. And so the plot command now also gets that data, and we can plot it. Now, we can continue this piping story here. Let's say we also want to save our plot here to disk. Okay? Well, we can pipe. So VL plot returns a plot. I can save the plot. So I can save the plot as a PNG file. Okay? Note that I'm again using the same save function, right? So the save and load story here works for tabular data, but it also works for the plots here. Okay, so I've saved it as a PNG file. So if I look here, there's a figure 1 PNG, and yes, it saved the plot that we just created. All right. Maybe I want to save it in multiple. I want to save the plot in multiple formats. Well, I can do that as well, right? So this here will return nothing, but I can put that into a T. So at that point, it's still piping the plot further, and then I can say T, save it as figure 1 PDF, for example. And because I've put it into a T here, it will pipe it still further, and it will display the plot still. So this one here, what does it do? It loads data, it filters it, it saves the filtered data to disk as a CSV file, it creates a plot, it plots the file as a figure 1, continues to pipe the plot, saves it as a PDF, continues to pipe the plot, and then the plot is shown. So if we open this one here, then there should be a PDF file here that is also the plot. Note also for BigAlight, all the nitty-gritty details, like does it show in every front end, like iJulia on the REPL, in Juno, in VS Code, does it save in all the file formats? That I think we've squared that all. I think it should always just work out of the box. Yes?
File formats, you might cover this. How does it get the file formats? It's using the extension?
It's using the extension.
Is it the MIME types in your browser? Or?
So it's using the extension, and then from an extension there's a mapping to MIME types. And so the save function here actually, just if I recall this correctly, has a mapping from the file extension to a MIME type, and then it using the normal display show methodology to figure out whether the thing that it got supports that MIME type, and then it uses that to save things to disk. Okay, so that was the pipe. Any questions about that? Yes?
I was So is it because you can also use it to define kind of local variables to use later on in the pipeline?
I don't remember. I added that a year ago, and back then I presumably thought it had to be a macro for some reason, and I don't remember why I did that.
But I guess because you said earlier that you can put any expression inside.
Yeah.
Yes, and you can pass any expression as an argument to a function.
Yes, that's the reason. Thank you.
I don't vote either. That's guessing.
All right, so the next thing I want to talk about is actually the core of all of this, and that is query itself. So I should say the way this happened is that I started with creating the query package, and then all this other stuff that I've shown you so far sort of emerges naturally out of the design of query. That was actually not my plan when I created all of that, to start to create file I/O and stuff like that. But there's the core architecture of query, which, by the way, I think is one of the most genius designs ever. And I'm not talking about myself. I'm talking about the link design, which was created by some of the, I think, best computer science people at Microsoft and in academia. So this comes out of the functional programming universe. Eric Myers and a whole bunch of Microsoft research folks created that architecture, and it's just fantastic. And so I wanted to port that to Julia, because Julia is actually a really perfect match for that design. And then at some point you realize, oh, there's this powerful core idea in the link design that actually enables all these other things. So that's how this sort of spiraled out of control. So let's look about queries here. So this is a typical query that you might have. So you might load some data here from disk. So that returns a table to you, or a sequence of named tuples, the way I've shown it here. You might pipe it into a filter operator, query operator. So that will return a filtered list of named tuples. And then you can pipe that into an order by story. You can specify by which column you want to order things. And at that point, you, again, get a sequence of named tuples that is now ordered in a certain way. So at each stage here, what gets piped from one stage to the next is sort of a table, and then you can apply further manipulations there. So yes?
And for the order by short questions, and can you also, it was asked earlier in a bit different context, does it pass it back to the source whether it has index or not?
So the question, I mean, I think I'm always supposed to repeat the questions for the audience in the world. The question was, can the order by command here figure out that if you have a source that has an index, can it make use of that? So this is a similar question to what you've asked previously. You could write a backend for a query that makes use of that information. So the design here, the architecture is there for that, but I have not written that backend, right? So right now it does not make use of that. But I don't know how much work it is, so you be careful about that. But certainly it's sort of, all the pieces are there to do that. So let me show you that example. So we say load data cars feather. We pipe it into a filter here where we filter out anything that's not from Europe. And then we say order by, and we order it by horsepower, for example. And that returns a table again that is now filtered. Note that at this point it's not returning a data frame, right? It's just returning something that, again, is a table. And then it shows that. Now, queries. The example I've showed you here is an example of a tabular query. But query is actually not at all specific to tabular data. So these query operators that I showed you work on all sorts of data. So here I have an example where I'm starting out with a range, the numbers 1 to 8. I'm going to filter them, and then I'm going to order them. Okay? Same story applies. Here I get the numbers 1 to 8. They get passed to the filter story. It filters out all the uneven numbers. And then I'm going to order them in a descending order here. So note a couple of things. This underscore, the arguments to these operators, to filter and order by descending, they typically operate on one element in the input sequence by a time, and the underscore references the current element in that sequence. So in the previous example, the underscore stood for each row, and that predicate would be applied to each row individually. Here, it is going to be applied to each number in the source sequence, and the underscore stands for each number. So you write your filter condition as essentially an expression that takes one element from the input sequence, and that is referenced by the underscore, and then you can just write something that returns a Boolean value. And the same is true for order by descending here. I say order by descending, and then underscore, that means just order it by the numbers that you get here. Let's do that actually here in code. So I say 1 to 8. So that's a range. And then I say filter like that. And then I say order by descending. And now I have a typo. Descend. But why is there? No, there's some other problem.
Yeah, it's equal 0.
Yes, thank you. Okay. So what does this return actually? So if I the question, so if I pipe this into typeoff, you will see that it actually returns something from within query, right? So it shows as if it is an array, but it is actually not an array, what's returned here. It is sort of an internal object from query. But maybe I want to have this as an array, and then I just say collect at the end. I pipe it into the collect statement. Because the thing that I'm returning here from this query part here is an iterator. That's it, right? So an iterator you can materialize into an array by passing it to the collect function here. So in that case here now I can get a proper array. But we're not restricted to ranges, right? So let's start with a dictionary. Let's say we start with a dictionary where we have 4, B2, and then C. So here I have a dictionary with 3 elements. The keys are symbols. The values are integers. I start with that one here. Now I pipe it into a filter operation here. Now, what will the underscore stand for in this case? It will stand for pairs, because that's sort of the natural, that's what a dictionary iterates, at least right now. That might change, I don't know. So I can say I want to access the key here by indexing into the second element here, which is the value. And I can say I want that to be larger than 3. So what this returns is a query that returns 2 pairs, namely the 2 pairs that passed the filter. I can collect that into an array. So now I have an array of pairs. But of course, I can also pass this to a dictionary constructor again, because a dictionary constructor accepts an iterator of pairs. So I can recreate a dictionary out of that again. I can start from a generator. This is sort of silly, but why not? So let's say I start out from a generator here. So this is sort of a standard Julia construct. I can pipe the generator into another filter. Now, obviously, you would use the filter statement really in the generator, really, but in this case. But I just want to sort of show you that this all works. And then I can collect it into an array. So that also works. OK, so that's just to show you that these query operator commands actually are not specific to tables. It just happens they also work really well with named tuples, and so you can use them to manipulate tables really well. But under the hood, query actually doesn't know what a table is. It's actually quite ironic, because it's sort of so generic that it can just sort of deal with any stream of data here. OK, I think someone had a hand. Yes?
Coming back to the previous example with the array, so what does query actually does? Does it save the indices that it should keep? How does it work? So is it better for me to keep the query result and use it later? Or is it better to collect it if I want to use it?
So it depends. When you so the direct return of any of the query commands is actually. Can I hold that question because I'm later on going to talk about how this works, and that I think will clear that up. Yes.
So is it all restricted to working with the current element? Does it have memory? Can I look back and forth?
So the commands I have right now only, I think, it depends really on the command. But it's something like this one here cannot look back and forth. The filter command and the map command, I haven't shown you the map command, but the filter command and the order by command only operate row by row. There are other commands that group things, for example, that are a bit more powerful. And there's precedent from the link world where lots of other operators are implemented that have, so, for example, lagged operations and things like that. But that is not implemented at this point. Yes?
Kind of related, I know the answer to this. Let's say some sort of web application. Let's say you can get data from London, but the bus is on Tottenham Road. You've got this workflow, so when you refresh your browser, it would reread in some data dynamically. I mean, it would dynamically update. Say,
oh, okay.
Buses and
You're tempting me to talk about something that I've been thinking a lot about, but so this is just what it is, right? So it will run. I will show you later on when the query will run. If I have time, I might get back to your scenario, because there's actually a very, very cool design around this for data that gets pushed. Data that is actually, so this is all, yeah, I'll get, if I have time at the end, I'll get back to that. All right, so I think the next thing I wanted to do is I wanted to just talk about a couple of specific query commands and introduce those. I think I should probably speed up a little bit so that we get through all of that. The first one we've already seen, that's the filter query command. It's sort of one of the really commonly used. So you pass it in just some condition, and any element from the source sequence that satisfies that condition will be passed on. But maybe this is sort of a good time to take a specific look at the syntax that's used inside here with this underscore and how that works. So let me go back to my slides. Because the truth here is actually the following. What something like filter here accepts as an argument is actually an anonymous function. So what it really needs is an anonymous function that takes one element, and that anonymous function needs to return a bool. Okay? And that's sort of the filter condition. The same is true here for order descending. What it actually needs is an anonymous function, takes one element, returns something else, and then it will be sorted by that something else, the sequence. And this underscore notation is just shortcut that only works within query operators right now, within these macros. But I think there's hope that this will actually make it into the general Julia syntax at some point. It's a shortcut to create anonymous functions. So how does that work? Well, so if you just write an underscore, it actually gets translated into an anonymous function, like the one. Is there a? No, you cannot see my pointer. The first line, right? The first line here on the right-hand side, it gets essentially translated into an identity anonymous function. If you write something like log underscore, it gets translated into an anonymous function that gets one argument, and the name of the argument is underscore, and then the log function gets called on it. If you write something like underscore dot foo equals 3, it gets translated into an anonymous function that takes one argument, and then on the right-hand side, the condition is written down. So essentially, when you write something with an underscore as an argument to any of these query operators, it will take that expression, put it onto the right-hand side of an anonymous function, and use the underscore as the argument name for that anonymous function. But you don't have to use anonymous functions. So you don't have to use that syntax. So we could obviously also just write this out by hand. So we could say something like filter and write the anonymous function out manually, right? And that also works. So this is really just a shortcut that we're using here. OK. So let's go to the next command here. So I'm going to say 1 to 10. The next one is a map. I think most of you are familiar with maps from base. So this is essentially a projection. What does it do? It takes each input element, applies the anonymous function that is the argument to the map, and then returns a sequence of values of these transformed elements. So here I'm going to say map underscore squared. So I'm taking every number that is passed in, I'm squaring it, and I'm returning a sequence of these squared numbers here with the map. Now, the map is really powerful because it allows us to return different types of elements. So what I can do here, for example, is I can say, start with the numbers 1 to 10. Now, inside my map, I'm going to actually create a pair. So I'm going to say, create a pair for each input element. The key of the pair should be the number, and then the value is the number squared. And at that point, I have a sequence of pairs. And a sequence of pairs I can pass into a dict. Right? So I can now pass it into a dict. All right. So how does this work with columnar or table data? So let's say we start out with cars. I pass it into my map function. The underscore now stands for an individual row, and an individual row is represented by a named tuple. So I can say map origin, and that will return a sequence of strings here, for example, okay? Because that's what I've extracted from each row. So let me very briefly do a detour about named tuples. Or just does everyone know what a named tuple is here? Because then I could just save myself that. Who is not familiar with named tuples here?
I would like more about them.
I know that you know what they are.
I didn't know that I know what they are.
Okay, so I'll be very quick with that, okay? But there was a question before I do that.
Touches a bit on the early stuff. Like, say you have a map followed by a filter.
Mm-hmm.
Will we be able to do that, like broadcast, fuse that internally without?
I'll get back to that. So if you have two things that are so a sequence of that, it is actually a lazy implementation. It will be fused automatically. Yeah. But it's still not ideal. Because, we can talk about that later. Okay, so let me do a brief detour about named tuples. So if I say cars, and I pipe them into collect, so what will that do? Well, cars is something that is an iterable table, so it iterates named tuples. If I put that into a collect, it will return an array of named tuples. So now I have a 406 element array, and each element is a named tuple. And so let's look at one individual one here. So I say nt equals r1, the first one. So this returns an individual row. So this is essentially the type of thing that you get passed onto as the underscore if you use query. If I look at the type of nt, then you can see it's a named tuple type. And then if I look at the field names of a named tuple, you can see here it has one field for every column that there is. So you can think of named tuples just as anonymous types. So it's like a type, a struct, but it doesn't have a name. Okay? That's sort of the story of that. And then you can access individual fields here just by the dot, with the dot operator. Named tuple's origin here will return that specific thing here. You can also index into them like normal tuples. So nt3 will return the third element in that named tuple. So the dot operator and this indexing in here are kind of synonymous.
That's 07.
No, this all works on .6 because the named tuples package on .6 provides all of that for Julia.6.
What about the missing values when you load the data?
So I'll come to missing values later on. It's everyone's favorite topic. Man. The short version here is that this uses data values to represent missing values. Okay. There was another question somewhere? No. Okay. Great. So the next story is there's a shortcut syntax within query to create named tuples. And that you mostly use that within a map. And it works the following way. So if you use curly brackets within a query operator, it will create a named tuple. And the syntax is as follows. You say field name equals the value, field name equals the value, and field name equals the value. Okay, so this would create a named tuple with 3 fields. The first field would be called field name 1, second field name 2, third field name 3, and so on. And then you assign values to these specific fields. And then it supports 2 shortcuts. So the first one is if you leave out the field name for a certain thing, so like this one here, it will just use the name of the variable that you're passing in here for the field name. Okay, so this is sort of a shortcut. And that also works if you access another named tuple here. So this syntax here is actually synonymous for the second column here. It will automatically use the name foo here because that's the name of the that you're using to pass it in here. So with that equipped, we can use map now to create streams of named tuples out of other streams. So here I'm starting with the numbers 1 to 10. I'm going to say map. And now in the map, I'm going to create a named tuple by opening curly brackets here. The first column here is going to be just the number. And the second column here is going to be the number squared. So at this point here, I'm returning a table again. Right? So I've transformed my sequence of numbers into a table because I'm now returning a sequence of named tuples, and that's a table. Okay? All right. And now at this stage here, I can sort of do I can save it as a CSV file, I can plot it, and so on. Right? So in some sense, Query really bridges the world of tabular data and the world of custom types or anything else. Right? So as long as it's a sequence of things, you can use Query to go from one to the other. Yes?
I was curious whether it needs to be a named tuple to work with Query. So say I have my own struct that has a bunch of field names. Can I also use that, and can I collect that as a data frame with a column per field name?
So to collect it into a data frame at the end, it needs to be a named tuple. But you can use this with a collection of persons, your own, and use Query on that. Query doesn't care, right? So Query itself is not tied to named tuples. You can use any custom data structure and query it with Query. And then you can use Query, for example, to at the end transform it into a named tuple so that you can then actually save it as a tabular file format. Okay, so now we can use that to do a whole bunch of sort of typical manipulations that we want to do with tables. So let's say I have the cars data set, and I just want to select a subset of columns. Well, I can write that like this here. So why does this, and that will return only these two columns out of my table with many more columns. How does that work? Well, for each row, I'm creating a new named tuple. The named tuple gets two columns. It's auto-inferring the names for these columns from the columns that I'm selecting here. So it's automatic. This is sort of equivalent to writing name equals. And so I've selected a subset of columns here with map. I can also use this to rename a column, for example. So if I wanted to rename the year column here, I could say foo equals. So in this case here, I'm specifying an explicit name for the second column, and then I get a table with the column names name and foo. And so at that point, I've mentioned this already. Because this is a table now, I can save that obviously as a cars 11 CSV file, for example. Okay, so I'm going to skip this. So that's the map command. Any questions about that? All right, so let's move on, and I really should speed up. So the next command is drop. So drop drops the first three elements from the input sequence and then returns everything else. So that's relatively straightforward. There is an equivalent take command. So I can say drop the first three and then take the next four. So that returns four elements. So this is sort of like a paging type functionality. That obviously also works with tables, right? So I can say drop the first three rows from my table type and then take the four next rows, and then I get a smaller table with only 4 rows here. We've already seen sorting a little bit, so I can say cars, order by origin, so that will sort the table by the origin column here. If I want to sort things the other way around in descending order, so then I can say order by descending. And then it orders it in the other way. If I want to, sometimes I have situations where I need to sort by multiple columns because one column does not because they're ties if I sort by that. So here I say order by origin, but there will be rows that have the same origin. And then I can say then by year. Okay, so any column, any two rows that have the same origin should then be sorted by year. So that's how I can do these sort of nested sorting things, and I can continue with that as much as I want. So I can say then by year, and if there's still ties, I can say then by descending, let's say horsepower. Okay, and then I will it will sort it in that way. Yes.
Since you have all of it covered, you have one where you can extract with the unique values. Say I want to filter out, take only the one line that have a unique item.
You could probably use the unique function from base, and it would probably just work, but I'm not sure. Yeah. Yes.
Does take short circuit?
Yes, I think it does, if I recall. Okay. Now, just one thing to highlight here is that this sorting business is not restricted. If I sort a table, I'm not restricted to sorting it by columns. I can do the following, for example. I can say sorted by the length of a certain column. So why does that work? Well, actually, what it does, the underlying design is simply it's an anonymous function that returns some value for each row, and then things will be sorted by that. But there's nothing, you can call any Julia function here, right, to go arbitrary crazy. So here, I'm actually going to sort it now by the length of the string in the origin column. So you can put any arbitrary transformation in here by which you actually want to sort things. Okay, so the next thing I'm going to talk about is grouping. All right, so we start out with a table, and then we have the group by command, and it takes an anonymous function, and that anonymous function returns a value for each row that we get, and then we'll group the input rows into groups that have the same extracted value here. So here, for example, this anonymous function extracts the value of the origin for each one, and then it creates 3 groups for the 3 distinct values that we have in that column, and then it will place the rows that correspond to each of these groups into these 3 groups. So if we look at the code for that, I say cars group by origin. Sorry. Origin. Now I'm getting something really weird and ugly. Because what we're getting is a data structure that represents each of these groups. Okay? So this is not very helpful. So typically with the group, after the group by, I actually want to do another map to extract the things from the group that I actually really care about. So one thing that I can extract here, now remember the underscore here stands now for each group, because that's what I'm piping further here. I can say underscore key, and that will give me for each group the value by which I grouped. Okay? So in this case here, I'm actually extracting the 3 strings that made up the keys of my groups, so USA, Europe, and Japan. But I can also look here, for example, at the length of each group. So I can call length on each group here. So the underscore here stands for a group. And then I see, oh, the 3 groups have these many elements here. I could do a silly thing here. This is sort of not very robust, so I don't recommend that. But I could, for example, extract the 3rd element out of each group. And now I have a table with 3 rows where from each group I took the 3rd element. Now this is not robust code because you might have a group that doesn't have 3 elements, and then this would break. I can do my map here and actually create a new table. I could say the origin equals underscore key, and the count in each group is length underscore. And then I need to close the parentheses here. So now I've created a table that summarizes the groups that I've created here. I think, all right. I'm going to just show it to you like that here. Like with the sorting, I'm actually not restricted to just group by the values in the columns. I can group by some arbitrary transformation. So I can group it by the length of the origin column, for example. Okay, so here we have, if I group by length of origin, I only get 2 groups because actually there are origins with 3 letters and origins with 2 letters, and so I can create a different type of grouping. I'm going to skip over that now. Okay, so the next example is the following. Yes?
Typically, you would do some math over the group, like average minus.
Getting there.
How do you
Get a minute. All right. Okay, so now if we want to summarize each group, right, in some way, there are 2 ways to do this. So the first one is we can actually specify a second argument to the group by function, like this here. And this second anonymous function will get applied to each element in the source sequence before we put that element into the group. Okay? So here I'm grouping by origin, and then I'm saying, actually, what I want to put into each group is just the value from the MPG column. All right? So at that point, I'm creating 3 groups again, but the elements in each group are now no longer named tuples. They're individual floating point numbers. Okay? So what that allows me to do is the following. I can say, let's say cars, group by origin, and then let's say acceleration, and then I say map, and then I say origin equals underscore key, and then I say the mean acceleration for each group. I can now just call mean on the group, because the group is actually an array of the elements that are in that group, and now I made the group to contain only floats. So the underscore is an array of floats, so I can call mean on it. Okay? And so now I've created a table that summarizes the average value for the MPG column for each group.
How is it an array if it's still called underscore.key?
Yeah, it's a type grouping. It implements the abstract array interface, and then it also implements this. That's the only difference to a normal array, that you can access key. But it is actually just an array. Yeah. Yes?
Is it limited to just one field value?
That's where I'm going next. Okay, so this is cool if you just want to summarize one field, but what if you want to take the mean of 2 columns, right? Then this strategy won't work because you will need to put at least 2 columns into each group, and then you can no longer call mean on it, right? Because now each group is actually an array of named tuples, and you cannot call mean on an array of named tuples. So for those cases, we actually need a different strategy. That strategy is the following. I will go back to my original thing, where each group actually has named tuples in it. So each group is a table. And I'm going to modify my map statement somewhat. So I'm just going to copy that. I'm going to take out this projection part here in the origin by. And then here in map, I need to change that slightly, because the underscore now stands for each group, and each group is an array of named tuples. And now you can use the following syntax. You can say underscore dot dot acceleration. So what does that mean? It is essentially saying the underscore is an array of named tuples, and dot dot acceleration says extract the values from the acceleration column here. So now I'm getting a stream of floats, and I can take a mean for that. And now I can add another mean to that, right? So I could say, well, I could say mean else equals, and then I can, or I don't know. Let's say we take the min acceleration. We could say something. I don't want to go too far that, but it's sort of clear that with this model here, you can actually summarize multiple columns at once. So let's try whether that works. And it does. So what does this dot dot notation do? That is sort of something that is query specific. And it works the following way. An x dot dot y expression in a query is actually translated into this type of generator expression. So it's essentially like, yeah, it's a generator, right? It's a projection. So it says, for each element I in the source x, that's the thing to the left of the two dots, extract what's the I dot y, which is to the right of the two dots. Okay, so that's sort of how this is actually under the hood working. With Julia, the Julia.7 version of this, we'll actually get rid of that, and you will just be able to say x dot y. Because with the property overloading, I can actually implement this in a much more elegant way. Yes?
I have a question. What if your column identifiers, either source or target, are not valid identifiers?
You're in trouble.
Okay.
Yes. I think you could okay, so I think you could index. Yeah, I haven't thought that through. But I think you could probably index into the name tuple with either positional arguments, but not with this syntax, right? You can actually write out a map manually here, and that would work. Yes?
Does it support the function blocking like do blocks? Instead of just mean, you have several statements and then block passing.
I don't really understand that.
It's like usually there's function blocks where instead of making it out, you can place it like embedded inside. Because, right, for example, you have mean, which is just one line.
Yeah.
But you need, for example, several statements.
Oh, whether you can, probably, I'm not sure. At some sense, this just gets translated into normal Julia code, and in most cases it works, but I haven't tried it. Yes?
Can you do a then by after a group by, like you can do with order?
No.
Could be.
Does that make sense? I have to think about that.
You can group by two columns together.
Oh, yes. So you can group by two columns. Yes, you can. But it's you can do the following. You can actually create, for example, a named tuple here, underscore origin underscore foo, and then it will group things by that named tuple. So I think that's what you wanted to do.
Well, I mean, you could use the same interface, like with the then by, because it's
Yeah, I'd have to think about it, but that's sort of how it works right now, right? Because you can have an arbitrary function that returns something by which you group, and so you can just return a tuple or a named tuple of multiple columns, and then it will be grouped by that. Okay. So I'm tempted to skip the next thing that I want. I have to stop at 1 sharp, right? Is that I think that's probably the idea. So why don't I do the following? So there's this is all documented, by the way. So you don't. This is sort of you can just go to the documentation. The next thing I wanted to show you is how you do joins, where you can combine two tables. It's pretty much how you would expect it to be. So I think I'm just going to skip that in the interest of time. And if I still have time at the end, I can go back to that. But at this point, I think I want to move on to other things. So yes, so I'm only scratched a couple of the query operators. There are more. There are things like join. There are things like group joins. There are things like flattening operators, map many, which is sort of, for those of you who are into monad world, is like a bind operator. There's a whole bunch of other operators, and I'm probably forgetting some right now, that are all documented and that you can also use to manipulate these data pipelines. So the next thing I wanted to talk about is when is processing actually happening with this? And we've sort of touched on that a little bit, but I wanted to go into a little bit more detail for that. So I'm going to write a query out here that loads something from Feather. And then it's going to pipe it into a filter, USA. And then it's going to pipe it into a map where I select just a subset of columns here. And then I'm going to pipe it into take, and I only want to take the first 5 rows. And now I'm putting in a semicolon here. Okay, that's really key. And I'm executing this line. If I do that, nothing is happening. Okay? So no processing is happening at this point. Because what this is building up is actually a data structure that describes this query, but it does not run the query. Okay? So there's a distinction between these two phases here. So Q now holds an object that describes this query in a declarative way, but it has not executed that query.
But the load is executed, yes or no?
No, it's not executed. Okay? And I'm specifically used feather here as an example because that's the one area where this really works. Okay? Nothing is executed here. Okay? I put in the semicolon because if I hadn't had put in the semicolon, a show method would have been called, and the show method would actually have processed things. So, but I really wanted nothing to be processed here. Okay? So now I can say for row in Q, because Q is an iterator, right? And I could say print line row. And at this point, when I run this, it's actually going to execute the query. And in this example here, it's actually going to execute the query line by line. Okay? And so now let me show you how that works here in my slides. Because I created nice slides for that. Okay, so when is processing happening? Everything is lazy in this design. Okay? So here's our for loop that I just wrote. And the for loop now runs for its first iteration. So the first iteration for loop asks the thing that was returned by the... this example is sort of slightly incorrect. Imagine I did not have this take element here, so I'm just showing you this pipeline for the map and the filter, but not the final take pipeline here. So the for loop is asking the instance that it got back from map, which is an iterator, for the first row. It says, give me the first row. The map iterator is now asking the filter iterator, give me your first row. The filter iterator is going to the feather file implementation and asking, load the first row from disk. Okay? So at that point, the data is, one row is being loaded from disk. That row is returned to the filter iterator. The filter iterator is checking the condition. It's realizing, oh, the first row actually should not be returned. It's going back to the feather file implementation, asking for the second row. The second row is returned. The filter checks the condition, realizes this row is good, returns it to the map. The map applies its transformation, and then that is returned out to the row. Okay? And then we start over. So everything here is fused in the way broadcasting is fused, and everything is lazy. So if you only ever... and so in the example that I had in code, it only loaded the first 5 rows, so it will actually only load as much data from disk until it had 5 rows that satisfied the condition here. Yes?
Do you have parallel computational streams?
There's nothing parallel in here, but there's precedent for that. So the link architecture that Microsoft had actually had query backends. One version was a p-link provider, and another one was a dryad link provider. And one automatically parallelized queries onto threads, and the other one automatically parallelized queries onto clusters. So the architecture is there. It's just a lot of work to get that right. And that is certainly areas where if people wanted to contribute and chime in, it would be fantastic. But I think that's sort of one of the things about query. The design is such that it enables a gazillion things, but that's too much for me to handle, right? So if people want to help out with that, it would be fantastic.
It's mimicking exactly what you said, what's found in Link, what's found in Java streams.
Yeah. So this is a copy of Link. So let's just be clear, right? So query is a copy of Link. You will find a one-to-one mapping of almost every single concept. Okay. Let me show you this one final code example here on this lazy loading story. So this query in particular, data cars feather, and then we filter it. Wait, I think I can just copy that, right? So I filter that, and let's save it as a CSV file here. Cars 12 CSV. This is sort of the ideal case because the feather source supports this. And the feather source, I should say, it only works because of that great work that I only know his GitHub handle, Expanding Man. Is that person here? No, he wrote the arrow package, and that is sort of really cool. So this query here, it loads something from a feather file, it filters it, it maps it, and then saves it out as a CSV file. This never loads anything into the whole data set into main memory. It streams it completely through, including the whole query pipeline. All right. Any questions about that? I want to use the remaining time for plotting because that is also cool. OK, so we're starting out with our cars data set. Let's do the minimal plot that we can do here. So I'm taking cars, and I'm piping it into a VL plot command. And I'm going to say I want to use points as my visual elements on my canvas. And that's it. OK? So what this will do is it will create a plot that will create one point for each row in our data set. So how does that look? It looks like that. Well, it drew a point for every row, but we didn't tell it how we wanted each point to be positioned, so they're all drawn on top of each other. So this is not a useful plot. But now we can go from there. So we can start to say, OK, actually, the x property of the point we want to pick up from the gallon column in our input data set. Okay? So now we get a graph here where we still get one point for each row, but they're spread out on the x-axis because we've encoded or mapped the x-axis properties onto our columns. And then this pattern continues. I can say I want the y property of each point to be mapped to the acceleration column. And now at that point, I've created a scatter plot. And so in this way, I can map lots and lots of different properties of these visual marks that I'm putting onto the canvas here to data from a specific column in my data set here. So here I can, for example, say the color I want to be the origin. So at this point, I've created a plot that has a legend where each point reflects the color of each point reflects the values in the color story. OK, so let's go a little bit further. I'm just copying that. Let's say we want to split this up even more, and we want to create a faceted plot. So I can say the column of this plot here should oh, no, I actually wanted to do the hold on. I wanted the color to be cylinders, and the column to be the origin column. Okay. So what I'm doing here now is I want to create one plot for each value in the origin column. So I bound the origin column to the column property of my plot here. So I've created a faceted plot here. So we've briefly talked about this already. Maybe we actually want cylinders to be plotted not as a continuous scale, but maybe we actually want that to be a nominal scale so that it just looks visually different. So I'm changing this here to a string, and I'm saying cylinders : n to signal to BigAlight that I actually want this one here to be plotted as a nominal scale. And at that point, the color scheme is different because it is no longer an ordered set of values. It's just a nominal set of values, and then you get sort of nicer stories here. There was a question, yes?
Is it possible to change the axis titles?
Sure, yes. You can, OK, so in this case, if we want to change the axis titles, I actually want to specify more about the x thing, the x property. So I'm not passing in just a column name. I actually want to pass in a composite thing. So I'm going to use curly brackets here. The first positional argument here is still the name of the column I want to encode. And then I can say something like foo here to change the name of the axis here. And this starts to look a little bit like JSON. You might be able to see a link there. And this is where the link to BigAlight is fantastic, the underlying package, because it has a gazillion options here, and it's all documented, okay? It has a really good documentation. So you can actually just go to the BigAlight documentation, look up all these things, how you want to do that, and then in a relatively easy and straightforward way, translate that into configuration options here, and it will all work. Okay, so what was the plan here? Going to skip this in the interest of time. I think I should skip a whole bunch of things here. So you can, there are lots of properties for each mark that you can do. We could encode here that we wanted to use a different shape for each thing. So for example, I could say here I want the shape of each point here. I also want to be based on cylinders. I need to put a comma in here. So now we get also a different shape for each element. And you can go crazy and look into the BigAlight documentation. There are lots and lots of options there. We can also create other types of plots. So I can say cars, BigAlight plot. I can create a bar plot here. I can say the x-axis should be miles per gallon. But I actually want to bin it. And then I can say the y-axis should be the count, the number of elements per bin for each element here. So that way I can create a histogram here. And then I could split that up into a facet plot in the same way. I'm going to skip a lot of stuff here now. So I'll post a script which has many more examples of that online. But essentially, I think this is a grammar of graphics syntax that is, in some parts, it has more features than ggplot, and in some other things, it has a little less, but it's very comprehensive, and it is very well documented. Not by me, but by the people that built sort of the underlying technology. OK, so then let's say we save this plot into P as P. So P now has the plot. You can save plots. I showed you this already with the save function. So you can say foo PNG. This also works with, you can save it as PNG, PDF, SVG, and EPS files. You can also save it as a foo BigAlight file. This is a JSON file that is in the BigAlight syntax. And Jupyter Lab, for example, natively supports that. So I can just double click on that, and it will open the plot, because Jupyter Lab actually supports BigAlight files. OK, last thing. Let's pipe our cars plot into Voyager again and save the return value of that in V. OK, so it's opening up a window. V now references this interactive window. So it shows me a couple of default plots. So let's say I want to start with this one here, and I want to select this plot as my plot here. So that's the plot I've selected. And now in my code here, I can say V, and then I can index into it. And it will extract the plot that I created in my interactive tool back into my Julia environment. OK? And it will plot that here. And the thing that I've returned here from the V square brackets is the same type that I can create with the VLPlot command. It's indistinguishable. So I can save this into a file. I can save this, for example, as a BigAlight spec. So essentially what I'm doing here is I'm extracting the BigAlight spec, and I'm saving that as a JSON file on disk, which is a description of how the plot should look like. And now I can do the following. I can, for example, say, I can load that also from disk. So I can say foo BigAlight. So I'm loading a description of a plot here, and it will show. And now I can do the following crazy thing. I can say cars. I filter my cars thing by saying origin in USA and Japan. So this is a filter condition that I'm using with query. And then I'm piping that into the plot that I load from disk. OK? And now it will show me a plot that I declare. So I created the plot description in my interactive tool. I loaded the declarative description of that plot into a file. I took a different data set, filtered it, and piped it into the plot description that I just loaded from file again. Okay? So this is really powerful. Think about a sort of typical paper that you write. You create a plot description. You save the plot description onto disk. Now you want to recreate the plot with new data. You can, that's the workflow that you want to use here. Okay. All right. That was my plotting and visual exploration. See, I managed to run out of time for missing values. Hooray. That was very much on purpose. So where are we? This is sort of my summary. So I feel that the basic design for all of this has really kept up well over the last 2 years. So I started with all of this 2 years ago, and I've added things, but I think I did not have to change anything fundamental because the core design over the last 2 years in JuliaLand has really kept up. And I think the reason for that is that I just copied something that had been really successful for 2 decades in the computer science field, right? So the underlying design, I think, is really solid. There's a lot of stuff in terms of convenience that is missing right now in terms of query operators, especially when it gets to selecting subset of columns. The map thing can get really cumbersome currently, okay? Now, the reason why that is not better right now is that there was no way to do this with the NamedTuples package in Julia.6. With the new NamedTuples in .7, that limitation is completely gone, so I actually expect, that's sort of the next thing I want to do, to add commands like mutate from dplyr and things like that, where you can say add 1 column, but keep all the other columns, things like that. So that will come, but that is sort of cumbersome right now. The performance, I think, of all of this is decent right now, with a gazillion ideas of how we could make things a lot more performant. That will require much more manpower than I myself can do, so anyone sort of more than welcome to participate in that. There's one thing here. The current implementation has a nasty reliance on inference. That sometimes means that all of a sudden nothing will work. It's frustrating when that happens. I have a very clear idea how I can get rid of that. And I think the version that I will tag for that works with 0.7, hopefully soon, I think that I will be able to actually get rid of that. So that's, if you run into that, I know how to get rid of it. I just need to do it. Some of you might have seen a different syntax for link, for query with these from blocks. There are actually 2 front-end syntaxes in query. I've today showed you only the piping story, which I by now like better than the old one, the one that I started out with. But the old one will stay around. I will not take it out, right? So with all of this, I'm hardcore about backwards compatibility. So the reason is I have a lab with lots of students, and I force them to use that. And if I tell them every 9 months, sorry, things broke, they will go crazy on me, right? And rightfully so. So in general, all of this is really meant to stay the way it is, and things that work will continue to work. I don't intend to break anything anywhere. I mentioned this a couple of times. I think there's a huge potential for alternative backends that automatically translate queries into SQL statements, backends that automatically parallelize queries, that maybe distribute them on a cluster. All of that is sort of there in the design, and there is literally implementations in other languages that do that we just need to copy, right? So this is not a question of coming up with good ideas. It's really just a question of taking what's out there and implementing it. And then maybe the last point here, as you can see, this is, at this point, it's sort of scarily comprehensive, and it's getting beyond the point what I can do by myself. So any help with the packages would really be greatly appreciated. And that's it. Thanks a lot. And I think so I don't know the official thing, but I'm happy to take questions. So why don't we start in the back there?
You pushed away a question on what's the closest to reactive programming you can push stuff to.
Yes, reactive programming. That's a great question. So the underlying interface here that sort of pipes everything together is the iterator interface. So that is an interface where the sink pulls rows from the source. So essentially, the thing at the end says, give me the next element in the sequence. And then that goes one step, and it sort of triggers up. In the .NET world, where all of this comes from, that is represented by the IEnumerable interface, which is the exact equivalent of our iterator interface. And then Microsoft created, I think in around 2010 or so, they created the mathematical dual to an iterator interface, which is the IObservable interface. So it's exactly the same story, but the other way around. Okay? So the thing on the left-hand side pushes elements out. And because both of these things are monads, both the iterator and the observable interface, you can write queries over observables in .NET. So you can have a source that is a push source, and then you can write a complete query, and it will actually push things through the query, and it will just reverse everything. So I've started a little bit on that to define an interface that is sort of the dual to an iterator interface, which is a push interface, an observable interface. And I think I got 3 or 4 of the query operators to work on that. So you can actually, at that point, think about a source, for example, a ticker or something like that. And you could have a ticker, you could write a query over it, and the query would run whenever a new element comes out of the source, and then it would trigger the query. So the design for that is really there. But the implementation is, at best, a very early prototype. But I think that's actually it's just cool that the whole structure of this accommodates sort of this other interface. And I think it's one of those, the reason it does, I think, is because people have thought about these types of reactive, very smart people have thought about the underlying design there for a long time. And I'm in an enviable position where I can just copy that stuff. There was another question. Yes?
Looking back to your last talk, you just spent 2 hours proving to us that American V8s use more gas.
That might well be true. Yes?
I really like this data explorer. Of course, you're linking to another thing, but you probably know it pretty well. Is there any hope that they will add a web interface that could be one day actually in a notebook?
So this data explorer is actually a web application. And what you see here, it is surfaced through an Electron window. The people that built the Voyager, that's the tool, so that's all the University of Washington team, they actually working with the Jupyter people to put that into Jupyter Lab. So that will actually become part of Jupyter Lab, and at that point I'm pretty sure there will be some easy link so that you can use that from a notebook directly. Yeah. Anything else? All right, thanks a lot. Enjoy lunch.